Matthias, good morning. Glad to see you. Here's some others coming as well. Alessandra and Alicia, good morning. And Kiara, Kai, and Malta, good morning. And Stella, Sina, and uh, Amelie, good morning. And a bunch more. Timothy P, hello. Hannah, good morning. And Leo, good morning. Great. And I've got Aslan, Aaron, and Clara, good morning. And Aaron. Good. I got Felix, Linus, and Tim H. Good morning. You're coming quick. I got Sophie, Corsine, and Jack. Good morning. And I've got Isabella, Inessa, and Ingrid. They all start with I. How interesting is that? Good. And I've got Isaiah and Paul and Zach. Super. As I've got also Charlotte and Corey. Nice. 9F is almost complete. And 9E is about halfway there. Let's see if we get a couple others coming in. We still working? Yeah, we're still working. Yeah, there's a couple other. And Felix, I think I had you already, but yeah, I do. Thank you. Good morning, Felix. So everybody, as for joining in this morning, and thank you for showing up so early. As for joining in, I'd like to start with a bit of a question, I guess. Been talking to other teachers, and we just kind of want to know how you're doing. You guys have been in lockdown, you've been online teaching for quite a while, since mid-December. It's not easy for us as teachers, and I'm getting the impression it's getting kind of hard on you students. Now, I'd like to have you guys share with each other, first off, how you're doing, and second, if there's any, what could I say, if there's any tools that you've got that you use to help you keep sane, okay? Like I will go outside and go for walks, or I'll go and play with a cat. What do some of you do? How are you keeping sane out there? And in general, how are you doing? We teachers are wondering. Hello, Cassidy. So, any feedback from you on how you're doing? Isaiah goes out and plays basketball. I love it. Okay, that's good. Even in the cold, tough. Very nice. Yeah, that'll keep your mind off worrying about stuff. That's a good active thing to do. Lesia bakes a lot. That's a good hobby to get into. And Amelia says she's doing okay. And Erin spends time with her family. Okay, that's good. Kiara does a lot of sports, and that's a good release, I think, for many of us. Alessandra draws. All right, an artistic person. And Aslan gets out and moves a bit. Hannah's a skater. That's great. She's had a good year for skating. Sometimes that's not the case here. Good, Hannah. And Kai, like Alessandra has been, no, Kai, like Alessia, has been baking a lot. That's cool. And healthy meal planning. Nice. Corey plays a lot of video games. I'm guessing, Corey, you're not alone there. And Charlotte also draws. That's a good relaxation. I like it. And I need to know who Jim Tucker is. Who is Jim Tucker? Are you in my class? And Alessia plays with her dog, it sounds like. Ayala is there. Good morning, Ayala. What does some of you else do? Inessa also draws and is redoing a jacket. Ah, very talented person. Can do some sewing as well. Ingrid is reading books and playing with a cat and dog and a lot of baking. Isabella's reading. Very good. I've read a lot of books in the last couple of months too. And Sina also draws. So I've got a lot of artists out there. That's nice for me to know. Ah, it's Tim H. Okay, thank you, Tim. I didn't quite know who that was. Thank you. Very good. Okay, another reader is Aaron. And knitting. Okay, another person with some sewing talent from Charlotte there. All right. Yeah, exactly. Well, I hope you guys are doing well. It's like a marathon, except we don't know when it's going to end. I've run a marathon, and you're pretty burnt out at the end, but at least you know when it's over. With this, I think part of the hard part for me is we don't know when we're going back. We don't know if we're going back full time. We don't know anything other than over the next week or so. Yeah, exactly. Right. We try not to murder people at home. Right. Michael, good morning. So, anything? Oh, I got some other comments too. I missed those. Ah, okay. And Zach's a musician, so he's been practicing his music. That's cool. That's another good relaxation piece. I do that sometimes with the guitar. Yeah, that would be great, Alessia. Sewing some gowns, some surgical gowns for use for people. That would be pretty cool. I know a lot of folks I knew as adults, my sisters and stuff, used to make masks for people, but now we mainly use the better masks that we buy. So, is there anything as teachers we can do to help you, to support you? So think about that. Anything we as teachers could do to help or support you. I've got a couple others. Kiara plays violin and Alessia plays piano. So some musicians there. That's good. I play a little piano as well. All right. Well, if you think of some things, let me know what I can do or what we, the staff, can do. We want to have our students mentally feeling all right too. And I know it's not easy. I definitely know that. All right. So just back to business a little bit. I'm still missing Isaac, Devante, Anton, and Ethan. And 9F, I'm missing Liam, Abram, Allie, Julius, I know where he is, Lauren, and that is it. I'll put this aside. And I do have some suggestions from you, so let me pause and you can stick to the schedule more. Now, the only I try to stick to the schedule, although I try to combine you 9E with 9F because that makes my life, quite frankly, a whole lot easier if I can teach you two together in my live streams. So that's why I do that. But at least I try and tell you ahead of time, Isabella, when I planned it. And if you have another teacher using that hour that has that hour at that time, I will respect that for sure. And Alessia suggests posting the assignments Sunday or Monday so we don't have to check as often and plan our week ahead. Yeah, although the problem with that, Alessia, is sometimes we don't know how far we're going to get in a live stream, so we can't always post something to do until we've covered the ideas a little bit beforehand. But ideally, yeah, I try to do that early in the week. Maybe the teachers could do a homework help for a few subjects if you don't understand something. Ah, Lauren, you have to say hi, so I know you're there. Okay, so I got Lauren. I do have Abram, and I do have Ali. All right. Everybody has to say hi when they come in, because otherwise I don't know you're there. Good. Okay, then I missed that, Lauren. My problem there. Okay, very well. Let's go ahead and start then with some physics, and I'll take your thoughts to heart and think about what Kiara said. If there's some sort of homework help we could do. If you have questions about the assignments I give you, you can, of course, write in the stream or write me an email, and I'm happy to answer you, okay? I do try to get back to you pretty quickly. Stay on top of my emails. Okay, you have an assignment that I think is due later today, and I just want to review again how this goes with the three types of reactions for radioactive decay, right? When I got something in the nucleus and it comes out, and that's because an atom is unstable. We'll see why that is in a little bit. Maybe we got that far last time. I'll have to take a look. Okay, let's warm up a little bit. The assignment's due tomorrow. Thank you, Inessa. Okay, so it's due tomorrow. So I see a few of you have done it, but many of you have not. So let's review the three types, okay? So I'm going to do some fill in the blanks, and you guys are going to help me out. So do these now. You need, gang, a periodic table, because this one's too small. You're not going to be able to see it. So find yourself a periodic table while I write up some. So I'm going to say, try these now. Number one. Goes to PA91, PA91, and 230. I'm going to make you go backwards this morning. See how if you can do it. Okay, so there's one. So see if you can fill in this blank. Number two. Goes to this. Plus, we're going to do CD, and that's 48. And let's make that 112. Let's make it 115. Good. So I'm going to have you fill in what you must have started with to get these products, right? So I want the reacting isotope. Remember that word? I want the isotope here and here. And let's do one more for grins. We'll do it in green. So goes to plus that's 63. And let's make that 152. Okay. So for 1, 2, and 3, what I'd like you to do is you can tell me the lower number, the upper number, and the element symbol. So you could say like, I'm going to make something up here, 22, 44, and whatever 22 is. Okay, and make up and give me the element symbol. So when you get an answer for 1, 2, or 3, let me know what it is. The mass number, the atomic number, mass number, and the symbol. So bum, bum, bum. So if you can put 3 things just in your answer line, you don't have to try and make them subscripts or superscripts, okay? Just put the 2 numbers and the element symbol, okay? And let's get some answers from you and we'll compare, okay? Some be right, some be wrong, okay? And you can write down 1, 2, or 3 so I know which one you're talking about. And I'll start looking and see with my periodic table if I agree and if all you guys agree. Okay, so for number, Aaron is there. Good morning, Aaron. Gotcha, Aaron. Okay, so I've got, I got some quickies here. Okay, so for the first one, I got thorium 9240. This is, that's gamma. So at least for number 1, your numbers should be different. So as far as I see, nobody has number 1 right. This is PA 91, and that's 240. And if that's gamma, that is not thorium. So try that again. Okay, a couple of you got it. Cassidy's got it. Good. And Alexander, it's the same thing. Remember, gamma means the protons and neutrons just shift a little bit, but they don't leave or change the nucleus. So this is still 91. This is still 240. And it's still PA protactinium, by the way, is the name of that, protactinium. So that one's the same. Let's try number 2. Number 2. And this is a big B. And then let's see if you can get that, okay? So number 2. Okay, I'm going to look. I know some of you got it already. I see Cena had it. And Cena, I think you got it. Let me just verify that. Cena is looking good. Cena's looking good. And Aaron, I know you're here. I got you already. Okay, let's see if we got. Yeah, exactly, Kiara. So for the top one, PA stays the same because it was gamma. Gamma. Right, and then Sophie had that as well. Okay, so moving on to number 2, I got some guesses here. I got some guesses from Sophie, and I think, Sophie, you're right. Yeah, I got that, Sophie. And I got a guess already for number 3. I haven't even looked at number 3. Alessia, you're way ahead of me. Good. And Kai, I think you got 2 right as well, as does Alessandra. Okay, so let's look at 2 real quick. 2, remember if I go, I still got the same top number for, this is beta. beta decay. The top number stays the same, so it's still 114. The bottom number, a neutron changes into a proton, so the bottom number gets bigger, so I have to go backwards to 47. Weird, huh? I made you tough. I made you go backwards. And 47 is indeed, as a lot of you knew, it's silver Ag, so that's an isotope of silver. Hooray to all of you that got that. Well done. Okay, lots and lots of you had that. Alexandra, Kiara, Aslan, and so on. Okay, let's look at 3. And I'll give you a hint. You can just about guess. This one is an alpha symbol. So you got to go backwards now. Can you go backwards? Yeah, good. Some of you are. I like it. I like it a lot. Good. Yeah. Like Lauren, I think she might have it. Let's take a look. So alpha, I lose 2 protons and 2 neutrons. So I think Lauren, you got it. I think it's got to start out with 65, and the top number has got to be. I lose 2. I lose 4. I lose 2 protons and 2 neutrons. So I think Lauren's got it. The top number got to be 156. Right? Because I got to lose 4 from that. So let's see who that is. 65 is TB. Is that right? It sure is. And I don't even remember what TB is. I'd have to look it up. It's not one I use very often. Well done, Lauren, and several others. Sina had that as well, as I think Alessia did, and I kind of lost her. She was so quick. Yeah, very good. A lot of you. Thank you. Thank you. Do you have questions on how to do these? I think you can do them backwards and forwards. Terbium. Thank you, Kai. Super. So we got a little terbium isotope for our for number 3. Appreciate that very much. Good. Good. Okay. Do you have any questions on the assignment? The assignment is to like identify some reactions and then do a bunch of alpha, beta, and gamma type reactions. So if you haven't done it yet, please do it by tomorrow. Today would be a good day to get it out of the way. All right, especially now that you're kind of fresh up with it, right? Remember how to do it. Good. Anything else from you before we change gears and get to our topic of the day? Then I think I'm going to get our topic of the day started here. Our topic of the day is talking about half-life. I'm going to write it over here as like an objective. We'll see what that is, and it has a bit to do with mathematics as well as physics, but the math is not hard. Don't get all worried. You okay here? I'm going to erase this now. Yes, Ethan, I got you. You're all set, Ethan. Okay, so yes, here we go. What is a half-life? Okay, so kind of goes like this. Radioactive isotopes what I'm going to say is going to sound like it doesn't make sense, but it's actually what they do. Radioactive isotopes decay at a fixed rate, but individual atoms may like give off their particle, may undergo radiation whenever, okay? So I'll say, but it varies when individual atoms decay. You know what the analogy is? And it goes like this, folks. How many of you have made popcorn? Okay, I see a lot of hands out there. Just kidding. If you made popcorn, this is kind of what it's like. You know how the kernels start to pop, but you can't predict when each individual one is going to pop. But they're kind of once they start going, there's a regular rate. It's not perfect analogy, but it's a pretty good analogy. So you really can't predict when an individual popcorn kernel is going to pop. But you know, most of them are going to pop. That's kind of what it's like with radiation. Okay? So a half-life and sometimes scientists just write it like this, half-life, like the fraction 1/2. It's the time for yum. Yeah, good, Isabella. Schrodinger's cat. Yeah, that's another story, but a nice story. Okay, half-life is the time for half of, let's make it the time for half of a radioactive sample to decay to something else. Sounds wimpy, but that's kind of what you got to say because you don't know what they're decaying to. Could be something that's still unstable, could be something that's now stable. Let me read that, see if it makes sense, okay? All right, the half-life, the time, yeah, for half of a radioactive sample to decay to something else. Now, these can, well, let's see if we got a question. Let's see, you'll have to try it out and find out. I have no idea. I'm guessing no, but I don't know the answer. Okay, half-life times. So these times vary, and I mean they really vary. Like you may have, by the way, the symbol for half-life is this. I might as well tell you this in case you get in chemistry. It's T to the 1/2. 1/2 is a subscript, okay? So these times vary. For example, there are some half-lives that are so short they're measured in a nanosecond. So nanoseconds. And nano is 10 to the -9th. In other words, it would be like 0.0000001 seconds. Can you see what I'm saying? So a tiny fraction of a second. So nanoseconds, or there's some that take billions with a B, billions of years. They decay very slowly. Are you going to have to know a half-life? No, not generally, unless I give you data to figure it out. We'll give those items to you, especially if it's an exact number of nanoseconds or billions of years or something, okay? We'll give you those items to think about. And it really varies. For example, I could have a type of uranium that might have like a 1,000,000-year half-life, okay? And we'll see what that means in a second. And then once an individual atom decays, maybe it's still unstable, and the next half-life in its little series of decays might have a half-life of 3 seconds. Boom. And then the next one might be like 20 days, and the next one might be 1,000,000 years, and the next one might be like 45 years. So they really vary. And a decay series can take a long time. Remember, a series was a number of steps. So if I'm radioactive, it may take several steps until I get to be stable over here. And the steps can take different amounts of time. Each step has a half-life. Isn't that wild? So it really varies. Okay, we're going to think about that mathematically in a moment. Let's see if I've got um, any other comments. Alessia, good. The belt of stability. I meant to finish that up. I'll have to go back and finish that, but I haven't yet. How do we know something's stable or not? When it stops emitting alpha, beta, or gamma radiation, Kiara, then it's stable. So there's no way for you to know that. You have to have a way to measure radiation. And I'll try and do that at school in a demo with you and show you that maybe this week sometime when I'm at school. Why is it only half a radioactive sample? You could make it whatever. You could say when the Kiara scientists could have said when 10% of the stuff decays or when 90% of it decays. But you know what? Half ends up being pretty good because of the mathematics that I'm going to show you now. Okay, let's get to the math. So here we go. I'm going to erase this. I'm going to give you a math analogy, okay? So it's a little like this from geometry. So geometry analogy means it's kind of like this. Let's say we got a block of radioactive stuff. And let's say that a half-life has gone by. So we got one half-life. What that means is half of this stuff has decayed to something else, like this. Okay? Well, let's let a second half-life go by. So I'm going to draw the same box. I'm going to abbreviate half-life because I'm running out of room here. I'll say HL. Okay, well, half of it has already decayed. But a second half-life has gone by, so how much of it is left, everybody? So I'm not done drawing here. How much of it is still undecayed? This one, half of it decayed. If a second half-life goes by, how much is left undecayed? See if you guys can answer that. I'll move this over so you can see the whole board there. More important than me. All right? Good. A lot of you got it, including Inessa and Timothy P. and Kai and Aslan. A fourth is right. So here we go. So half of this now will decay in the next half-lifetime. Let's do one more. So a third half-life. And as I'm writing, why don't you type in how much would be left of the original sample after 3 half-lives have gone by. So I got in, I got in. So after 3 half-lives, how much is left? Thank you, everybody. Good participation. Yeah, I got that from Paul and Isabella and Aaron and several others. 1/8 is left. So now I've got to take another chunk out and say, well, the half of that's gone too. So we got half, we got 1/4, we got 1/8. And that, you see how it's very mathematical? I always just divide it by 2 again, don't I? Half, fourth, and eighth, 16th, 32nd, and so on. So what that means is this. Let's make our example a little broader. Let's say we had 100 grams. So I'll say example 100 grams. So how much is left? So here we'd have what, 50 grams left. 50 grams of my 50 grams of my radioactive stuff left. Here I'd have 25 grams. Here I'd have 12.5 grams. And I'd go on and on. Let's graph that. So I'm going to go time. But I'm not going to go time in time. I'm going to go time in number of half-lives, okay? Number of half-lives. So let's go. And I'm going to make it real even. So there's 1 half-life. It's 2 half-lives. 3 half-lives. 4 half-lives. I wish I had a board with blocks on it. If you have block paper, it can look even better. And let's take, so this would be on this side, we're going to say amount of radioactive sample. And we're going to start right there with 100 grams. But that would be at 0. You know what I'm saying? At 0 half-lives, I've got 100 grams. Well, let's fill in some of these with a dot. After 1 half-life, I only got 50 grams left. So I got to go down here to half of this. So I got a little dot here. Or I'll put a little German X here. So I got an X here. I got an X there. After 2 half-lives, I got, that's 50. I got 25, so I got half of that. So I got like this. Whoa, that's 25. Okay, after 3, I got half of that, so 12.5. Getting hard to put that in here. 12.5 is going to be out here. And after 4, I'd have like 6, wouldn't I? Way down here. Well, I think you can see it's not a line like you might be used to in math classes. We're going to draw it together. I'm going to draw it in red. It's a curve, and it's supposed to be a curve. We did it correctly. It's supposed to be a curve. So draw it with me, all right? It's a really important curve. Draw it nice and smooth. Don't just connect the dots. Make it a smooth curve. So there's about as smooth as I could get. I wish I was a better drawer. I started out smooth, and then I got sort of crappy here, didn't I? Should be nice and smooth. Something like that. Now, you're going to study this in math class. Well, let me ask you, have you had this sort of looking graph in math class already? Can you give me a yes, yes, or a no, no? Does this look familiar in math class, or have you not had that yet? You might get in 10th grade. I can't remember. Have you had this sort of graph going down like this yet? Just a yes or no from some of you. Oh, some of you are saying yes. Ah, okay. Yeah, okay. All right, you've had it. Good. Okay. Then maybe you know what it's called. It's called a curve. And the name comes from nuclear physics. So somebody know the name for grins. Curve. Yes, Sophie, dynamite. Exponential. Curve. Let's see if somebody knows the rest of it. What does it say on the left side and bottom of the graph? Okay, on the left side, see it says amount of radioactive sample. And I got like 150, 25. So that's the amount of sample starting with 100 grams. It should be grams here. And on the other side, it's the number of half-lives, 1, 2, 3, 4, and so on half-lives that go by. Okay, anybody else got the rest of it? Exponential curve. Going once, going twice, gone. So it's called exponential decay because it's based on radioactive decay of radioactive elements that occur in nuclear physics. Isn't that kind of cool? Yeah. So anyway, it's an overlap between physics and mathematics, and there's a lot of these overlaps. Ute. Good. We're going to come back and do something mathematically with these. How are we doing on time? We're doing okay. But I want to finish up a topic I started last time, and then thanks to Alessia for reminding me. And it's about how to know if something's stable or not. Okay. All right. I'm going to just pause here. Questions about this before I erase it? We got one more thing to do this hour. By golly. Okay, and away it goes. Away it goes. Okay, so here we go. Elements, no, isotopes are, no, let's put it this way. Isotopes will keep decaying if they are not in the belt of stability. So we drew this before, and let's draw it one more time. So it kind of goes like this. The belt of stability is another graph, and it has to do with when things are, how many protons they got and how many neutrons. We don't really care about electrons for this. And I got to remember how this goes. I think it's number of protons on this side, and it's number of neutrons on this side. Now, if you look at the molar masses, you might remember from last semester, like helium is 2 and 2. You know what I mean? It's got 4, so it's got 2 protons and 2 neutrons, okay? So helium would plot like here. Boom, 2 and 2. That's stable. Carbon has 12. Well, that means it's got 6 protons and 6 neutrons. So carbon would be out here, 6 and 6. So there's like a 1-to-1 ratio here. Let's look at nitrogen. Atom number 7. Well, its weight is 14, so it's got 7 protons and 7 neutrons. So that would be in the same row. Let's look at calcium, Ca. Ca number 20. It's got 20 protons and 20 neutrons, so it's also in a row. This is the belt of stability. These guys are stable. But look at the really big guys, okay? Look at number 58. Number 58 is Ce, cerium, and it's got 58. But if I doubled that, it should have like 8 8 is 16, should have 136 as its number of its weight, and it's not. Its weight is 140. So what happens when I get to bigger atoms? Bigger atoms need more neutrons. So the belt of stability, where things are stable, starts out 1-to-1, but then as we go on a ways, with the bigger atoms, the belt kind of goes like this. So they need more and more neutrons to be stable. So here it's like, for you mathy folks, this is like a 1-to-1 ratio. And I'm talking 1-to-1 ratio for the protons, P plus, to the neutrons, N0. But towards here, we can even write that. We can say, hey, bigger atoms need more neutrons to be stable. To be stable. Now, most are in this belt. Yes, I know I've run out of time. Give me just a second. Most are in this belt of stability, belt of ST, stability. But if it's not in there, let's say it's out here, then it's going to start to undergo decay somehow or other to try and get into that. And sometimes it might have to undergo a couple decays. Until finally, once it gets in there, it's stable and it stops decaying. Okay? So unstable. So these are all unstable. And above, these are all unstable. You got it, gang? These will all decay until they become stable. And then they stop decaying. Ta-da! That is it. I'm going to pause for questions, but we've run out of time. Thanks for staying the extra minute. But that's what the belt of stability is about. Most of the atoms you and I are made of, and we see, most are in the belt of stability. Most things are stable, okay? Most stuff. But the ones that are unstable are out here somewhere on one side or the other of this belt to become stable. Let's see if we got any other questions. Exactly, Alessia. Okay, Sophie says wouldn't occur the other way. Did I screw up, Sophie? Sophie's right. Okay, so, oh man, all right. Those who already left, I better make this carefully. So, let's see, protons, neutrons. No, I think I got it right, Sophie. Let's see. I think it's right. So protons go up, and then I need even more of these. No, I drew it right this year. Sometimes I draw it backwards, but sometimes I do it right. This year I think I got it right, Sophie. Okay, everybody, thanks, and hope you can finish your assignments for tomorrow, and we'll tell you when your next live stream is. All right, have a good rest of your day. Bye-bye.